Welcome everyone. My name is Zhihua Xie from the Department of Aeronautics at Imperial College London in the UK, and this is the new episode of the podcast Turbulence at the exascale. If you're not familiar with the podcast, we are trying to gather the view of the community here in the UK regarding the challenges and opportunity associated with exascale computing with a focus on turbulent flow. So this podcast is linked to the UK Turbulence Consortium and to the UK ExCALIBUR initiative, which is a project led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to redesign our software to harness the power of exascale computers. So today we have a guest from Cardiff University, from the School of Engineering over there. He's a senior lecturer and his name is Zhihua Xie. And his research interests are obviously in computational fluid dynamics, fluid structure interaction, high performance computing, turbulence modeling, multi-phase flow, wave water mechanics, hydrodynamic, and so on and so on. So it's a great pleasure to have him today. So good morning, Zhi.
Yeah, good morning, Steven. Yeah, thanks for having me here.
Thank you for joining us today. And I'm going to start with my first question. If you can tell us a little bit more about yourself, where you are from, where you have studied, and how did you end up at the University of Cardiff?
Okay, so it's mainly, of course, I originally from China. So I born in the south part of China. And then I have all the primary studies and high school. And then I think for my first degree, I moved, I think, 2,000, I think, miles away from my home. So I moved to the northeast of China, so Dalian, for my undergrad studies as environmental engineering. So I stayed 4 years there, and then I continued for another 3 years for my master. It's mainly focused on the hydrodynamics. And then at the end of 2006, I have the opportunity, I think, about the Marie Curie Early Career Fellowship, I think, come to UK to further my PhD studies at the Center of Computational Fluid Dynamics at University of Leeds. And then I stayed 3 years there for my PhD. And then initially I moved to Cardiff University as my first postdoc, working on large area simulation for the rough beds. And then after 3 years, I have the opportunity to join Imperial College London to work on a program grant, working with Professor Omar Matar and Professor Chris Penn. So I stayed 4 years there, working on something different for finite elements modeling. And then in 2017, I rejoined back to Cardiff University, a lecture, and working with Professor Torsten is mainly for AES and then various aspects. And then, yeah, I stayed there since, I think, 4.5 years now.
Good, great. And may I ask you, how did you become interested in I would say, in computational fluid dynamics and studying turbulent flow using supercomputers? How did that happen?
Yeah, it's mainly traced back, I think, during my master studies back in China. So at that time, very interested in the math and also applied math modeling. So I initially had more interest I start from the diffusion equations. So one-dimensional diffusion equations, I get interest, and then move to the vacuum diffusion equations. And then very interest for different schemes and also the different high order, I think, the compact methods for different schemes. And then eventually I move on to more shallow water equations, and then to the Bosnian equations, because at that time more focused on the hydrodynamics. And then when I actually start to think about the Navier-Stokes equations, mainly I originally more interested in the stream function and vorticity formulation to solve the Navier-Stokes equations. And then the first equation, the problem I solved is the driven cavity, I think, which is the first benchmark. And then at that time, I didn't actually have any experience to solve the Navier-Stokes equation, use the parametric variables. So since I joined in my PhD at Leeds, I start to broadcast my interest So it's mainly start to look at more detail how to solve the Navier-Stokes equations, and also have the turbulence modeling, because I'm more interested for the breaking wave. So in breaking waves, we have to solve the Navier-Stokes equations, we have to deal with the interface captions, and we have to deal with the complex structures and the turbulence. And then at that time, it's mainly developed main focus on the RANS model, because at that time it start with the RANS model, and then start everything from scratch, and then gradually move on to Cardiff. It's may focus on the larger assimilation. Okay, so I brought a main from that time I get more deep into the turbulence. I think the communities I look at a lot. I think from in the UK a lot. I think from the Imperial and Southampton did a lot for I think the turbulence. It's mainly for the single phase. I gradually deep into that, and then but my focus is mainly have the free surface interaction with the turbulence. And then after that, I mainly joined to Imperial College, mainly do the different stuff for more small scale, which is have the bubbles and droplets. And then, yeah, and then when we back to Cardiff is mainly more interest for the fluid structure interaction. And then, yeah, gradually, I think, yeah, that's I have a lot of interest for different things. So it's mainly, that's the CFD and turbulence is mainly my central, my heart. So, yeah.
Great, thank you very much. So you have spent some time in Leeds, at Imperial College in London, and in Cardiff. And I was wondering, what do you like the most about working at Cardiff University, and how does it compare with Leeds and Imperial College?
Yeah, I think that is mainly because I think the job I think is fun. I have all the people surrounding me, which have a great fluid dynamists. So it's either in Leeds, especially in Imperial College, and also Cardiff. So it's mainly have all the people mainly for the working on the turbulence, and also in Cardiff, especially I'm mainly working with I think the professor Tim Phillips, which is mainly expert in non-Newtonian flows there, and also have a working with the professor I think at Elisabetta De Angelis. So it's mainly we'll have the students working on the turbulence and non-turbulence interface. And then she's mainly working on the detail in the turbulence statistics. And then I have the opportunity working with the Professor Torsten Stosser, which now he's moved to UCL. So it's mainly, yeah, just mainly I think through my journey I have been working with in Leeds. We have I think the director of the center, Dr. Training, Professor Peter Jimak. And also of course at Imperial have so many I think different people working on the CFD. I was very fortunate to meet some of the people there and then learn their experience. So yeah, that's I found it field unlucky. So working on different universities with different people there.
Great, thank you very much. Let's talk a little bit about your research. And can you briefly tell us a little bit more about the current projects you are working on?
Yeah, so it's mainly currently I'm mainly working on some project working on different aspects. So it's mainly for hydraulics. We have one EPSS project. It's mainly looking for the free surface flow over the rough beds. So look at the different roughness. We have the gravel and the spherical and the different kind of bed roughness. And then we have another EPSS program working on the free surface flow in the pipe. So which normally the turbulent, I think the multi-phase flow inside the pipe. So how to look at the fluid structure interaction. We have the sensors in the middle of the pipe to look at the fluctuation of the pressure and how that's deformable, and then yeah, something like that. And also in the other side, I also have some low society projects, mainly looking at the floods effects. So the flooding and impact on the peoples and on the different structures. And then yeah, and then I have my interest is mainly for the breaking wave impact. So it's mainly have the opportunities working with the professor I think Diaz in the University College of Dublin. So it's mainly he has the ERC advanced grants working on the wave impact on the coastal structures. So it's mainly we have collaboration. I'm doing the simulation there. And then it's mainly more interest for working with the professor, I think is in the Italy, Brocchini. So it's mainly his interest in the turbulence. We mainly focus on how the vertical structures interact with the interface and also the air entrainments. And recently, I think this year we just got another EPSSSC project. Is mainly working on the wave energy converters. So that's a collaboration with 5 universities. So we're working on the different potential flow and the CFD and combined with the machine learning. So the project will start in the 1st of September. So for 3 years, yeah, I'm looking forward for that. So that's mainly the current most part of my research.
Great. Thank you. Talking a little bit about flow solvers. So the main flow solver that you are using at the moment, it's Dolphin 3D. And so can you tell us a little bit more about, what type of numerical methods, in which language it is programmed, and how do you deal with supercomputers?
Yep. So it's mainly, this is the solver is I mainly developed since my PhD. So at that time, not like fortunate for like others, they can join a big group. They already have an established code they can use. So for me, I start everything from scratch. So it's mainly the basic is I have to continue to develop since my PhD, and then but I stopped. I think there's a 4 years gap. I didn't any development since I moved to Imperial because I working on another code called Fluidity. So it's mainly for the Dolphin 3D. It's mainly the name is mainly for the digital simulators for the turbulent multiphase flow through structure interaction. So it's mainly use the finite volume methods. So we use the Cartesian grids because it's easy. You don't need to generate the mesh at the beginning. And then we have the capability to deal with the interface caption. So because for the flow solvers, I will mention is use a static grid, staggered grid method in 3D Cartesian grids. So for the flows, for the velocity and pressure couplings, we use a pressure correction method. So it's either simple or the piezo skins. But solver we mainly have the implicit for the time stepping. So I think that's the main difference compared to others. So it mainly have the first order and the second order back order time stepping methods. And also for because I think the one challenge is mainly I use the conservative Navier-Stokes forms. So which is try to keep the mass and the momentum flux consistent. And that's challenge. So that's why mainly we have some high resolution skins for the reaction. So it's not like I think others for single phase of a high order. So it's mainly we combine with high resolution skins. And is the central difference for the diffusion and the pressure that comes there. And then I think that's for the Navier-Stokes solver. And then we have the capability for the interface caption. So because I'm mainly interested for the breaking waves. So in that case, the mass conservation is the key for us. So I mainly have the different version of the volume fluid methods. So ranging from the algebraic VOF to geometric VOF, and also to high order Plick VOF. And also recently we have in the development of the momentum fluid method to deal with the multiphase flows in that framework. And in terms of the how to deal with complex structures in Cartesian grids, so we mainly use the Cartesian cut cell methods. So which is have the strength to inform the I think the conservation and the consistency for the not only for the momentum equation, but also for the continuity equation. And that's the key, I think, for our research, because mainly we have to deal with the moving structures and deformable structures. I think especially for the moving structures, I think some of the Cartesian grid, you might find that there's the pressure spike, especially when you have the moving bodies there. Yeah. So that's why we mainly deal with that. So for the turbulence, it's mainly for the 2D, I use the Cape Center models, write everything from scratch, validate from the turbulent flow for the 2D channel flows there. And then for the 3D, I mainly focus on the larger simulation with the dynamics small scale subscript models there. And then for the high luminous, because for my focus is the civil engineering fluids. So when you have the high luminous, we actually cannot resolve. I think that's the y plus less than 1 there. So it's mainly we use the wall model areas approach for that. Because we have the cut there, we know exactly the geometries near the boundary there. So we can calculate the y plus and use the wall models there. And then in terms of the parallels, there's many, we also have the mesh, adaptive mesh refinements as well to refine in the vicinity of the structure and also for the interface. And in terms of the parallels, we use the three-dimensional domain decomposition approach, and then have the MPI for the parallel computing there. And then also in terms of visualization there, so for the inputs and outputs, we use the HDF file for the outputs, and I normally use the open source code, the visit, so for the visualization, and also to outputs, we can output the tagplot as well, and also I mainly use the MATLAB to do the data analysis. I think that's probably that's the picture.
Thank you very much. And I wanted to ask you, I mean, when you were working at Imperial College, I believe you were using the Fluidity code, and I think you have also been using Hydro3D. So how does Dolphin 3D compare with those codes? And can you tell us a little bit more about your experience with using those three solvers?
Yeah, so the three solvers are totally different. So it's mainly so that's why I get a broad range of the numeric method, and also have to learn different things as well. So for the fluidity at Imperial, it's mainly developed by the Professor Chris Pan there. So it's mainly the control volume and the elements formulation. So it's mainly the discontinuous for the velocity there, for the momentum equation, we have the dg, and then also use the control volume for the, I think for the pressure and also other quantities. So because he's have the advantage for using the anisotropic unstructured mesh refinements, so it can reduce computation efforts, but without sacrificing accuracy there. So it's mainly, before that, it's mainly for the single phase flow for the ocean modeling. So when joined there, so it's mainly try to develop for the, working on the multi-phase flow to develop, I think, implement the surface tension, have the balanced surface tension, especially for unstructured mesh, that's not easy. And then also we have to deal with how to deal with the bubbles and droplets and all kind of the multi-phase flow, both in the industry and also academia. So another code is when joined the Cardiff, which is the Hydro3D. I think is developed by Professor Torsten Sousa there. So it's mainly that is used the finite difference methods. So in terms of solver there, so it's used just I think the fraction step for the Navier-Stokes equations, and then it's the explicit skin, the longer quota for time stepping, and then for the interface caption there is the level set methods. And then to deal with the structures is mainly used the immersed body, which is the diffuse interface drag forcing methods there. So you can see all the three codes are totally different. So in terms of the methods, cover finite difference, finite volume, and also finite elements. And then in terms of the deal with structure, so the fluidity is fully unstructured mesh, so it's a body fitted. And then so for others is one is the immersed body, and then the other one is cup cell. And then for in terms of the interface caption, so it's the level set in the Hydro3D, and also for the fluidity, it's mainly it's the algebraic VOF methods. And then for my Dolphin 3D, it's mainly the geometric VOF method. So yeah, that's yeah, all the range are different. So
good. And I have a tricky question. Well, because you wrote Dolphin 3D, but which one of the code is you prefer in terms of user friendliness? Like how easy? Which one is the easiest, I will say, to learn and to run?
Oh, so that one will be, I think, easiest. I think probably depends on the application. So depends on application. I would say all the method have all the advantage and the disadvantage. So for the Dolphin, I think it's everything. So not for other codes, it has long developments for different people. So for the Dolphin 3D is everything, I think stuff by myself. So if you look at that, probably not easy for others to look at. So because I didn't have spent time to optimize the code and everything there. So but in terms, I think the different applications I will have a different using different codes for different. So especially if you have an anisotropic problems, so I think only for the interface, probably I think the fluidity probably is better because it can reduce computation effort a lot. But if you mainly look at, I think the turbulence structures, which you need fine mesh everywhere, probably I think is the structure mesh is better. But mainly, I think in terms of my view, I think our future is have to be the combined with high order methods, with I think the high fidelity simulations, and also with combined with HPC and with combined with some mesh adaptation. So I think the combination of three will be, I think, the powerful stuff. So and also we are actually thinking about, because I think we're talking with Professor Torsten Stoser, so because we both have the Cartesian grids, different frameworks, so we might think to merge to some one codes probably in the future.
Great, thank you very much. I also wanted to talk to you about a recent collaborative project in which you have been involved, which has to do with the a wave and a cylinder and the interaction between a focusing wave and a cylinder. So I've seen there are two publications with a lot of authors, and can you tell us a little bit more about this big collaborative project?
Yeah, so this one I think is originally from 2 years ago. So it's mainly originally from the experiments is performed at India Institute of Technology, Madras, and then we have collaboration with the City University of London, and I think we organize special sections in the ISOC conference. So we have 20 different group submit using their own codes, I think, to do this kind of problem, which we have the focusing wave, which is generated at the expanding flume, and the impact with either the fixed or the moving cylinders. So I think this community is slightly different from the turbulence communities, because most of the codes are mainly based on the open forms. So if you look at in the wave communities, most people use open forms there. So they're doing their developments, so based on the open form framework. So you can see, but mainly we try, there's a lot also the potential flows to simulate this kind of problems, because for that case it's simple because there's no wave breaking there, so you actually don't need the proper CFD codes, and also there's not too much, I think, the vortex shedding, especially when you have just a single wave there. If you have the fixed cylinder, but you have the moving cylinder, you will have the vortex shedding, which is downstream of the wake. So that main collaborative project is mainly end with, I think, more than 20 universities group in the world joins, and with 20 codes. So we have compared with the different the accuracy and efficiencies for different code there. So I think, yeah, we just gave a summary, I think, for what's the use for the wave structure interaction to community for that. Great.
Thank you very much. And a final question about your research. I've seen some work about acoustofluidic devices from you, and I'm not quite sure. Can you tell us a little bit more about this?
Yeah, so it's mainly, that's a slightly off track of my research. It's mainly when I joined my Cardiff, I think my colleague is mainly Dr. Chris Young. So it's mainly he's working on the experiments for deal with the cancer cells and the blood cells, how to do the magnification for the particles. So I have done some research on the microfluidics, but that one is a multi-physics. He's mainly asked me, can you do some simulation for this? How to, so it's mainly is combined with the surface acoustic wave, and combined with either the multiphase, the droplets and particles. So you can see, in addition to the multiphase, which is already complicated in micro scale, you have additional fields, either the acoustic wave, the pressure, acoustic pressure wave, or any, I think, either the temperature fields in addition to that. So it's mainly the main idea is try to use that to optimize, I think, the microfluidic device, and then how to separate different particles, and if you have the cancer cells within the small, I think, the microfluidic channel. So that's some kind of research and try to have this.
Great, thank you very much. I have a few more questions for you about exascale computers and exascale computing. And my next question is very hypothetical, but if tomorrow I give you access to a very large exascale computers, what would you like to study that you cannot study at the moment?
Wow, okay. So if I have that opportunities, so I will study so some things I think is my gene calculation. So because I studied my PhD is the breaking wave under the effect of winds. So in relation to that, I'm mainly interested for I think the net zero. So we have a lot of offshore renewable energy happening, especially in recent years. So I would like to start some simulation with you have the all simulation for the wave mechanics. And then we have the offshore floating wind there, so which is floating. We have the wind turbine. We have the tidal turbine. We also have the wave energy converters all in one go. So you can see we can try to simulate all the turbulent wave fields and also the wind fields, and then to resolve all the chromorphic scales for the turbulence, for the wave structures, and also all the bubbles and the droplets with the air treatments. I think, so if you have this kind of facilities, so that kind of simulation is I'm looking for.
Great, thank you. And do you think you will be able to do this with Dolphin 3D, or do you think you will have to change completely your numerical methods, or eventually you will be able to do it?
Yeah, I think it's mainly we are still in the development. You can see not like some other established codes. They can most deal with everything. So for us, it's mainly we have the multi-scale, multi-physics problems. So I think we can pretty sure deal with the interface caption. So we still try to improve with the even high order volume fluid method there. And then for the fluid structure interaction, we mainly can deal with the moving bodies. We are now working on the two-way fluid structure coupling, and especially have the flexible structures. And then I think the other ways is mainly try to understand the multi-scale problems. So we can, I think, even we have the actual scale computer, probably we cannot do the direct numeric simulations for that kind. So we need some, I think, substrate models there. So in terms of physics, so I think we are still trying to develop the substrate models. So for the turbulence, probably I think it's okay, but for the multi-phase flows, for the bubbles and droplets, I think we are working on the development there. And then so that's I think needs, because I think this is I think it's a challenge. So it's not, if you have the combine, even the subject project, if you have the turbulence, it's already a challenge. If you have I think the fluid structure interaction, it's also a challenge, even for the single phase, not. And also if you have the moving structure there, so we have the multi-phase. So that's, we need some time to deal with this, I think.
Good. Sorry, I forgot to ask you, or maybe you said it and I didn't listen carefully, but in which programming language is Dolphin 3D? Is it Fortran C or?
Yeah, it's mainly written in Fortran.
Fortran.
And then also there's some interface linked with C, is mainly for the linking for the input and outputs, that construction. Yeah,
and,
so the mainly part.
Great. And it might be too early because you said you are still developing the numerics, but do you have any plan for GPUs, or you are going to stick to CPUs at the moment?
Yeah, I think that's we definitely have the plan. So it's mainly, but my strategy is build everything step by step. So from the simple stuff to complicated stuff. So what we come from the journey is I normally start from the single phase without structure, and then add the structure, and then it's hand to the two phase for laminar flow, and then to the turbulence flow, and then add the mesh, adaptive mesh, and then the parallel, and then eventually we'll do, I think, I would like to get more skills for the computer science, try to combine with I think the CPUs and GPUs, because we use implicit solver. I think there's some way to couple with the CPU and GPUs. I think using the open, I've seen some work using open ACC. So to couple that, I think that's, and also optimize all the codes. I think that will be the next part. So when we already develop everything, develop all the physics and everything's working there, and then I think how to make it, I think the advantage used for the HPC will be the next stage.
Great, thank you. And I have one final question. It's a very hypothetical question. So we are talking a lot about exascale computers that will very likely be based on CPUs and GPUs of some sort. But I mean, you're still very young, so I can ask you this. What do you think will happen in maybe 20 or 30 years in terms of supercomputers? I mean, where do you think you will run your simulation in 25, 30 years? Do you think it will still be CPU, GPUs, or do you think we are going to have to rethink completely our software and we will have a brand new hardware? What's your view on that?
Yeah, so I think that will be a tricky question because we cannot predict the future, right? But one thing I can say is based on my experience. So when I start my PhD, I think is exactly 15 years ago. So I always, when I talk to my families, I always use my mobile phones. I also would like to have the video chats with my family. But at that time, it's not possible.
Mm-hmm.
Now you can see 15 years ago, everywhere we can use iPhones and Android phones. We can talk, join the conference and reply email, everything from the mobile. So in terms of that, I would like to think in the 20 or 30 years times, we can do our calculation, just use the mobile. So when we have the codes there, we just submit the job, and then the job will go to the cloud, HPC systems, and then come back with the animation. So I think when we do the HPC, take the data structure is very big. We have spent a lot of time download the data and then generate the animation there. But maybe in the 20 or 30 years times, we just click submit button, and then the animation, nice animation, will be automatically back to us. So I think, yeah, probably that's something yeah, I'm looking for.
That will be amazing.
Yeah.
Great. Well, thank you very much, Xie, for your input and for taking the time to discuss with you about your research and your view about high performance computing. We wish you all the best for your future development with Dolphin 3D and for your research. So thank you very much for taking the time to talk to us.
Yeah, thank you, Seven. Yeah.
No problem. And thank you everyone for listening to this podcast. As usual, the list of all podcasts with the speakers is available on the UK Turbulence Consortium website. If you Google UK Turbulence in one word, you will find us very easily. And of course, if you are following us on Twitter, it's UK Turbulence, once again in one word. You will find all the links on YouTube and SoundCloud for the podcast. So thank you very much, everyone, for listening to this podcast, and hopefully see you soon for a new episode.